The first thing I'm going to show you is how to calculate correlation. Correlation means a relationship between two things. So, allow me to show you this with a couple of graphs. These are some examples of correlations. When we talk about correlations, we talk about it in terms of an R value between -1 and 1. A relationship of -1 means that as one thing goes down, another thing goes down with it in almost perfect lockstep, right? Like, think of it as walking down stairs. As you take a step down the stairs, your height decreases the same amount every time. If we have a relationship of +1, we have a perfect increase or a perfect relationship. But we also have relationships in between, where it's kind of in the zone. There's a bit of a relationship as it increases. Sometimes the other thing increases at the same rate, or sometimes not at all. The data is just everywhere. In order to figure out what kind of relationship we're looking at, I wanted to see if your food scores relate to your favorite color choices. Now, I could average this and compare the average, but I don't really need to do that because I can measure with a correlation to see how it works out. So what I'm going to do is I'm going to use a formula, and you can grab your formula from over here. This is statistical, and instead of doing it like this, I find it's easier to just type the thing that you want to know. But we have over here Pearson's correlation. Okay, you don't really need to know how to do a Pearson's correlation in terms of calculating this stuff. What you do need to know is what it means. What it means is a relationship between two things. Relationships don't necessarily mean causation. You might like spicy food and like another color or a certain color for completely different reasons. But I wanted to establish, is there a possibility of a relationship as kind of a starting point? And oftentimes when you're doing research, this is how you start. You want to find out if there's a connection between thing A and thing B. Once you find out there is a connection, now you can start to investigate why. Are they actually causal? Is one thing causing another or the result of another? Or is it coincidental? So in order to figure out this correlation, very simple, I've got equals correl, then the brackets. Now all I need to do is put my data. I can take my food scores here, like that, then put a comma for the second set. Now it wants to know what I'm correlating against. It's going to be this right here. Then push enter. There's my correlation. A 0.23 correlation, it's weak. It's a pretty weak correlation. Now, there are some limitations on this data. I've only got 10 responses, which means that if one of you responded way outside of the norm or what the average person would respond in terms of their color and food choice relationship, that might be throwing the data off by a lot. We need to see if this is statistically significant, which is the next thing I'm going to show you. So right now we understand that there's a positive but weak relationship. So as somebody's color choice gets a little warmer, their food choice gets a little bit spicier. But it's not a very strong relationship. It could just as easily be that somebody's food choices gets cooler as their color choices get warmer. There's two things that I'm going to find out in terms of statistical significance. The first is standard deviation. This is going to tell me how far each response is separated out on a bell curve. A bell curve is something you're probably familiar with in terms of marks and perhaps other types of performance. What we're looking at here are a couple things. One, we're looking at the average or the mean score, which is right here in the middle. And we also see that most scores tend to be within 68% or one standard deviation of each other. So 68% of the scores all kind of clump around the middle. Half of them being a little bit higher, half of them being a little bit lower, but that's the average. Then we've got over here, one standard deviation is right here, two standard deviations over here, where we've got about 13%, almost 14% over here, and the same thing over here. And then three standard deviations. These are what we call outliers. They're way outside of the normal. Think of it like this. If we're talking about the current price of something, and we'll say the current price of a box of cereal is $5, and the standard deviations are 50 cents, you might go to one store and see that it's $5.50. You might go to another store and see that it's $4.50, but that's about the normal price. Maybe another store is having a huge sale on. They're selling it for $4. Another store is having some kind of crazy fire sale where you get them for $3.50. Likewise, way over here, we've got cereal now selling for $5 or $5.50. It may be some kind of premium store. The normal price for a box of cereal, if it's $5, most of those prices are about 50 cents away from each other. This is just a made-up example, but it explains what standard deviations are. The further out we get, the fewer times we see boxes of cereal way up at this price or way down at this price. The most common prices are here in the middle. We want to figure out what our standard deviations are. Before we do that, we need to figure out our total scores and then add them all together. We're going to use a formula here, and we are going to use our functions, find statistical, and scroll all the way down to standard deviation, which in this case is STDev. Now, anytime you see this, you can just type the formula. If you know it equals STDev and then the brackets, great, easy to do. So let's find the standard deviation scores here. All we're going to do is put in our numbers, and that's it. The standard deviation is 3.68. Rounded up to 3.69 by the look of it. This means that from one person's average score to another, if we're moving along this scale, if someone in the middle is right about there, we're going to move up 3.7 or down 3.7, and we'll still be within the average. Well, what is the average? Well, let's figure that out. We're going to go here to our statistical calculator. We're going to select average. And you can see here we've got the formula equals average and then the brackets, and we're going to get our average food scores. Our total food scores, we're going to average them out. There we go. We've got our data selected, and our total average is 10.4. Our standard deviation for this number on 10.4 means that somebody's going to go up to about 13, someone's going to go down to about 7. So now we've got our correlation, our standard deviation, and our average, and this can tell us a lot. The one thing that it doesn't tell us is this statistically significant? Are we actually looking at data that has meaning, or is it kind of a random collection of garbage? When we are doing science, and it doesn't matter what kind of science you're doing, we're looking for statistics that are at the very least, 95% reliable. If it's not 95% reliable, we, as a scientific community, don't accept it as statistically significant. So what we want to find out is this data here, is that meaningful? Or is it maybe a problem with our sample, or is something else? We are going to do what's called a t-test. So we'll call it t-score. And basically, this is a test that uses math to figure out whether or not the averages, or what the chances are of getting a mistake in your data are. When making a t-test, this is a little more complicated. I'm going to break it down step by step so you can understand what it means. First, our t-test is a function. You're going to type equals t-test, and then you're going to put in the data set, so a column, a data set, the other column, the number of tails that you have on your test, and the type. I will explain what each of these things mean. So first, our data set's pretty straightforward. This is data set 1 right here. I'll highlight that so it's easy. This is going to be our data set 2. And we'll put those in the equation. The number of tails. This is simply a number that you'll put in. So 1 for one tail, or a closed-ended question. A yes or no question is a really good example of a closed-ended question. In this case, I want to know if there's a relationship between these two things, your food score and your color score. That's it. But the way I ask the question changes things around. Because if we're looking at standard deviations here, and we want to know a one-tailed, right? We're basically discounting this stuff here and including all of this stuff here. If it's a two-tailed, we're accepting that it can be this way or this way, right? That we can have an answer that's way out here or way out here. What I want to know is a two-tailed question, because I'm accepting that there could be a relationship between these scores that is both positive or negative. So in that case, I'm going to put it 2. because I'm willing to accept that both your scores could be higher or lower. So the next thing I'm going to do is I'm going to talk about what type of test this is. There's actually 3 ways of doing this test. We have paired, unpaired, and a 2-sample or unequal variance test. The paired test is when you're measuring the same person over a period of time. Say like a before and after, or I wanted you to do this test before you took the lesson, and then I wanted you to do the same test after you took the lesson. So we're comparing a before score and an after score. The unpaired, generally we don't use except in special situations. And then the 2-sample test is probably what most of you are going to be doing. You're going to be comparing the results of one set of data against another set of data. So let's put all of this information in. First, we're going to type equals Ttest, then the bracket, then we want range 1, okay, comma, range 2, and now we want to select 2 tails, and the type of test is type 3, close bracket, and we're done. So, one point I want to make about this is that there is a really small data sample here, and small data samples mean there's usually a lot of data mistakes because one response can throw everything off. Using this data sample, and generally you need a minimum of 20 to do a good t-score. Using this data sample, we have a 0.00008% chance. We're going to change that into okay, so we want to have less than 0.05. This is obviously less than that. This is 5%, right? So this is minimal. And if you're not sure, change the number to percentage, right? 0.1% chance. This means our data is pretty reliable. However, it's questionable because we have a very small data sample size. But this is how you can tell if you have a reliable sample or reliable testing score from all of your work. So now we know a few things about this. First, we know that based on the 10 people that responded, there is a pretty weak but positive relationship between color score and food spiciness score, right? A few of you, or at least to somewhat degree, the more that you like spicy food, the more your favorite color tends to be a little bit warmer. Not a very strong relationship, but there is one. We know that the standard deviation is 3.68 for your food score. We could also check your color scores and see what the standard deviation is for that. And we might find that it's very, very little, right? You might move up 1 or down 1 on this scale. Our average score here, because we want to make this make sense, is 10.4, which means that most of you are around about a 3 when it comes to the average score of how spicy or savory or flavorful you like your food. And finally, we did a t-score to prove whether or not this is a statistically viable response. What we found out, if we ignore the fact that we only have 10 scores, is that, yeah, it actually is a pretty reliable response. There's less than a 0.1% chance that we've made a mistake, which is far below the 5% chance that we're willing to accept. So, when you're going through your information, make sure that you follow these steps, organize your data, clean it up, just get to the core of what you want to test, and put that on a separate sheet. Then start doing that statistical breakdown. Make things really, really easy for yourself. Make notes if you need to. And once you get those responses, question, does this data make sense? Is there any way that I made a mistake on this data? Is there any way my questions maybe led to this response rather than just me measuring what the possible response is? It's very important that when you're reporting your findings that you also consider the kinds of limitations your findings have. I hope this has been helpful for you. If you have more questions, please reach out. Talk to you soon.